Good morning. My name is Petr Novák. I'm a researcher here at Czech Technical University in Prague, CIIRC, and I will talk about the simulation and digital twinning for industrial systems. I will be focused mainly on the industrial zero systems, which are the new generation of the automation systems currently emerging in our and world industry. And despite the fact that in 4.0 is still some kind of a vision and not the real architecture or not the specific set the systems should fulfill. There is some kind of agreement or understanding, maybe is the better word, how Industry 4.0 systems should look like, what should be the requirements and what should they fulfill. And one of the most important requirement is the flexibility. And the flexibility should be fulfilled in products, production processes, and production resources, which means that, for example, one product can be produced by different production processes. It can be produced on different robots, which are the production resources. And all the production recipes should be modifiable, should be relatively flexible, changeable. There should be some kind of on-the-fly planning and things like that. But all these requirements lead to the fact that testing and tuning of such new generation of production systems is very difficult, and it's much more complicated than how it is right now, because right now it's possible to fine-tune all robotic movements, all operations. They are repeated many times, so it's relatively straightforward how to fine-tune all the thought data, all the recipes, and so on. So it makes sense to have some tool that will significantly improve the testing phase, and simulation models are this tool for testing and tuning the systems. Simulations are of course and they have been used many times, but right now with the emerging penetration of the Industry 4.0 systems in our industries, their roles is increasing. So I will talk about the simulations required for the system testing and tuning. But the second thing why we need right now simulation models is that new approaches for control based on AI methods, based on data-driven approach, need to be tested, validated, and it's very important to test them prior applying them in industry, because some of the patterns that are retrieved from the data can be wrong or can lead to some troubles in the real production, and it's very important to test them in advance. And simulation models are the useful tool for this. Maybe I would like to emphasize the difference between simulation models and digital twins, because right now we can hear and read many times about the digital twins. Simply speaking, the digital twins should be synchronized with the real system. The simulation models can be independent, can be run independently on the real data, on the real system. So typically the base of the twin is the simulation model, but it also includes some synchronization mechanisms to the states of the real system and of the simulation model inside the digital twin is synchronized in terms of the values of all states. Even though simulation models provide many benefits, their design phase is very complicated and time-consuming. Therefore, the benefits come after some relatively long design phase, engineering phase of the simulation model, and I will talk in this presentation how the simulation model design can be improved, can be done more automatically and supported by some algorithms. So if we are talking about the traditional design simulation models, doing in hand, partly on the paper, partly in the computer, we are starting with some mathematical physical of the system, plus we like manually go to the differential equation that describes the system. If we want to change the system, we need to embed some deeper decision rules or some dynamic model inside this model. It's very difficult to modify this equation. Therefore, it makes sense to go more in the modular way, and I will talk about this later. Very important comparison is here in the equation-oriented model that is here represented by the Modelica language. Then the equation-based modeling is not that interested into what is the input and what is the output of the model, but for the control purposes, frequently the signal-oriented simulator simulation are used, and here is the example of the MATLAB Simulink model realizing this edition. And in signal-oriented simulators, it's very important to decide what signals are on the side, what signals are on the output side, because all these decisions have to be implemented in the model and decided in advance. But or on the contrary, in the equation-based model, this is or decided by the solver. In both cases, it makes sense to remind the analogies that were introduced by the well-known Bond graph theory. This theory is approximately 50 years old, so it's like relatively well-proven and old from the scientific point of view, but it's still valid. And this theory defines the analogies, signal analogies, and connection analogies. So it enables to represent the equivalent signal types, like the voltage in electrical systems, the pressure in the hydraulic system, or for example the temperature in the thermal system, by the generalized variable called effort, and electrical current, hydraulic flows, and other variables as flow. and the product of effort and flow, this is the power that is transferred between the system components, or yes, system components or system devices, and this abstraction enables us to abstract from the system type and to support algorithmically the design and integration of the simulation model. So, for example, this particular example, we can see the pipe, pipe, which exists in the real world, and this real pipe can be simulated by one of the two simulation blocks. The first block calculates flow based on the pipe, and the second realization it calculates the pressure loss based on the known flow through the pipe. In case of the valve, we have just one realization of this simulation block. This is because it's possible according to the power loss, but it's not possible to do vice versa. So assuming this explicit representation of the available simulation blocks that we have for real device, we can then formulate the task of designing a simulation model as the combinatory task of combining the available simulation blocks for the given plant topology. So we are switching to the electrical systems, but as I introduced, the signals, effort and flow are abstracted, so it doesn't mind which system type we are talking about. And we have here some real system topology that has to be represented in the computer understandable format. On the next slides, I will how to represent the real system structure, for example, in the format called automation ML. But right now, let's consider that we have this real system description done in some data format. There is there has to be included what component in the real system. In this case, the voltage source, resistor R1, and other components, and also the topology connection components has to be represented there. Then we have to have the representation of the available simulation blocks, plus also the multiple realizations, like in this case, two realizations of resistor models. Similarly, like I showed in the case of the hydraulic pipe. And based on this information, we can utilize the abstraction specified by the bond theory, and to automatically transform this plant into the structure of the bond graph. The bond graph defines, as I said, the analogies for the parallel and serial connection as well. So this zero node represents the parallel connection. The so-called one node represents the serial connection. Plus, I should emphasize that this is the complete bond graph for this system, but it can be simplified according to some well-defined rules. So, for example, this zero node can be eliminated, and so on. But for the method description point of view, it's not important how to simplify the graph because the computer can calculate with the entire graph as we did here. And the thing is that in the classical bond graph structure, it's necessary to manually do the causality assignment procedure, but with this kind of formulation of the design of the simulation design process, we can or the computer can solve this combinatory task of trying to combine the available simulation blocks automatically by assigning the causality. It means these two bars on one side of each arrow, which specify what signal, effort, and flow is the input one, and what is the output one of the specific component or node. And based on this assignment procedure that can be fully automated and solved by computer automatically, we can then generate the simulation model for the given plant or cyber-physical system. As I mentioned, a very important part is the representation of the real structure. We are using the Automation ML data format for this. Automation ML is a platform-independent data format, which means that it's represented in XML and standardized by this IEC standard. Adopted by numerous industrial players, and here we can see the example of some Automation ML document in the Automation ML editor that is downloadable for free from internet. And Automation ML enables us to model nearly all system types that we want, but the problematic thing that we found was the relatively difficult or relatively high effort to represent the system, but we need to simplify the engineering processes to make them efficient. Therefore, we enhance the Automation ML data format with Python code injections and implemented the extended data format called PyAML, which is the abbreviation Python Automation ML. Maybe just to summarize, what information should be included in this real plant system description in AML or PyAML. It's the topology, including all components, list of all supported operations for all components, but also like some technical specifications about the endpoints, IP address ports of all components of the system, which are the pieces of the information that are supported and by Automation ML. There are white papers and recommendations how to represent these pieces of information in a standard or semi-standard way. But the problem is that Automation ML all nodes of this XML, Automation ML, have to include assignment of the so-called UUID, which is the unique identifier, and all the mappings among the components are based on mapping between two UUIDs. Therefore, it's very difficult to reinstantiate some kind of sub-models to reuse, for example, a description of one production line to the second production line, because then it means that we have to change all the UUIDs, because the mappings in the Automation ML data format is absolute based on these UUIDs, unique identifiers, and but for industrial usage, it makes sense to switch to some relative addressing to be able to reuse the descriptions of some system parts. And this is exactly what this is one of the features that Pi Automation ML is introducing. So with the Python code injection, we can specify, for example, the ancestors of on different levels. I mean, on the different level of the hierarchy. We also can use the lambda expressions in Python and other features of the Python language directly embedded in the Automation ML XML. Plus, we introduced some kind of Python preamble into the Automation ML or Pi Automation ML data format, where we can specify some initial setting or some initial, for example, import of libraries, or some specification of some global variables that are then used in the entire PyAML document. So with this enhancement of the original Automation ML data format, the querying of all information inside the plant topology, and this combination with the available simulation logs is then significantly more efficient, and from the development point of view, relatively simple. And yeah, we are using this kind of approach in different applications. So in the next session, I will talk about the modeling of the electrical microgrids, where we, for example, are instantiating the current electrical vehicles that are available in the garage, and yeah, also we are applying this kind of approaches in the testbed line that is here. So let me conclude. In this research I've talked about, we are trying to benefit from the simulation models and their integrated versions, digital twins. But we are aware that this design phase of the simulation models is very complicated, time-consuming, error. To simplify the design process of the simulation models to be able to use them in numerous AI applications and Industry 4.0.